Hello everyone, FPS Chazla here, and welcome to my, this is kind of like a random series, but coming up on my 1,000 subscriber count here, and I've had my job for a year now, which deals with nuclear stuff, so I decided to make a series about nuclear stuff. So, we're starting off today with particles, but I plan to go into reactor designs, radiation, accident analysis, all kinds of fun stuff, but before we can understand any of that, we got to start out basic here. So we got to discuss particles, and this is the basic units of everything that we're using to describe nuclear stuff. So this is going to be very different from things you see in the real world, because we don't experience these effects in our everyday lives, really, for the most part. Quantum stuff. I'm not going to get too deep into quantum stuff, but I mean, it is the subatomic world. We just don't have an intuition of it. So let's get started here. So there are 5 particles we're concerned with in describing a nuclear reaction. First, we're going to start with the atom. Yes, everyone's favorite little thing here with the, the electrons going around there. The atom. So this is the smallest chunk of an object you can have that still retains the property. So if you have a chunk of gold, the atom is as small as you can go while still retaining all the properties of gold. So that's what the atom signifies. That's why the atom is important. But the atom is made up of 2 parts here, the nucleus and then the electron cloud. Now, as you see it drawn here, it has these little distinct orbits, but that's not really how it works. This is just an easy way to visualize it. It's really a cloud, a quantum mechanical kind of cloud, if you're familiar with that. I'm not going to get into that right now, though. So the nucleus is made up of two particles called nucleons because they're in the nucleus. The proton and the neutron, denoted as such. You'll see them sometimes represented as a plus or a 0. That is because the proton has a positive charge of 1 and the neutron has a 0 charge, so neutral. So the number of protons you have in a nucleus is known as the Z number, or the atomic number, and this is what defines the element you were looking at. So hydrogen, denoted by H, has 1 proton and no neutrons. Helium, denoted by He, has 2 protons and 2 neutrons. So the neutron does not define what element you have. That's only the proton here. So the neutron, what it does is it provides stability to the nucleus. If you add the number of protons and neutrons together, you get the A number, or atomic mass number here. So all this is it basically tells you how many nucleons you have in a nucleus. So we add up the protons and neutrons in hydrogen, we get 1. So there's 1 atomic mass unit. Add it up for helium, you get 4, and there's 4 atomic mass units. So you may sometimes see elements denoted this way, like this. This number signifies how many atomic mass units there are, and not only does it describe how many nucleons there are, this is also what you use to describe an isotope. So an isotope is, since the element is not defined by the number of neutrons, you can have varying number of neutrons in an atom here. So you got your typical, I'm just going to draw it with this model here because it's just easy to visualize. So you got hydrogen 1, which is the most common form of hydrogen. You got your proton and then your electron out here. You can also have hydrogen 2. Don't really worry about the notation. It's very informal. Sometimes you'll see it written as this, or just hydrogen 1. But usually in my field, we would say H1 like this. You can also have hydrogen 2. So that would be a proton and a neutron with 1 electron. And this is referred to as deuterium, and will be represented by D. So this will be D2. And then you can have a proton and 2 neutrons with 1 electron, and there you will have tritium, which I don't know if people actually would say T3 or not. Deuterium is much more common with that. This is get into that later. So H3, hydrogen 3. So these are isotopes of a single element. You can have isotopes. You can have different numbers of neutrons. So that gets important later on. Also, the number of neutrons is referred to as the N number. So we have Z and N equals A. So Z plus N equals A. For a quick example, let's say we have uranium, which is element number 92, and let's say we have uranium-238. So using that formula from before, we have we have Z and N and A. So we know A and Z. So to solve this out, basically, you just get 147 neutrons. Just a quick example just to show how that works. And as you can see, uranium is a very heavy element, and this is a very heavy isotope. So there's 147 neutrons. So you can really see as you get up there, there's a lot more neutrons than protons in the nucleus, and that'll come into play later too. So let's move on to the electron here. Good old electron. The electron, in comparison to the sizes of the protons and neutrons I drew before, I'll just draw them for scale's sake. So this is your electron, basically. It's just a tiny little dot. So the electron is a very small particle. It's about 1/2000th the size of a proton or a neutron here. Yet it still has a charge of -1 compared to the charge of +1 for a proton. So that's pretty cool. That it's so small, yet it's still equal yet opposite in charge to the proton here. So in your ideal situation, the number of electrons is equal to the number of protons. So let's get ourselves an atom of helium. Here we got a proton, neutron, proton, neutron. That was a P. Got one electron here, one electron here. So this is a stable atom here. The electrons determine the chemistry of an atom. So we don't really care about that too much. All you need to know is if you kick out one of these electrons here, the resulting, so you'll have the two protons with only one electron now. So now this will be referred to as an ion that has a net charge on it. That's also a chemistry thing. We don't really care about that, except when it comes to detecting radiation, ions are very important to detecting radiation. So we'll get back to that later. So the electron is actually an elementary particle. Now that means you can smash it with as big of a hammer as you want. It's not going to get any smaller than that. The proton and neutron, however, are not elementary particles. They're actually made up of quarks. So you get one proton is made up of 3 quarks, and one neutron is made up of 3 quarks as well. The proton is made up of 2 up quarks and 1 down quark. The neutron is made up of 2 up quarks and 1 down quark. No, excuse me, 1 up quark and 2 down quarks. That's just fun to know. So we have what we call generations. I'm getting into quarks here. Generations of energy in the particle universe. So we have low, medium, and high energy generations. So in our day-to-day lives, we only ever experience low energy. So that's all we're concerned with. But I'm just going to go ahead and name these out because they're kind of fun. So low energy, we have your up and down quarks. For medium, we have strange and charm. And then high energy, we have top and bottom quarks. So these don't signify anything except for which generation these particles belong to. But I thought I'd just let you know that the proton is not an elementary particle. It's made up of quarks. But quarks are basically indivisible. So for all intents and purposes, going as small as a proton or neutron is more than enough for our purposes. So moving on. The last 2 particles we're going to discuss are the photon and the neutrino. That is not a very good nu. Some people like to draw their news like this. I like to draw my news like that. This is the Greek letter nu, not news. So we have the photon and the neutrino. Now the photon is not your typical particle like a proton or a neutron or an electron. The photon is the quantum of light, the quanta of light. So quantum, as an SAT word right there, and a very intimidating sounding word. What this basically means is your smallest form of something. So the atom is a quantum of gold, as the smallest form of gold you can get. So the photon is the quantum of light. That is the smallest thing that can represent light. The photon is what makes up the electromagnetic spectrum. I'm sure you've all seen this before. It's this thing that has this huge waveform, and then it gets very frequent as you get down here. So over here, so just to outline this again, we have radio waves, microwaves, infrared, visible, ultraviolet, X-ray, and all the way at the bottom we have gamma rays. So if you notice, this is the Greek letter for gamma. This is the third letter in the Greek alphabet. Yeah, yeah. Alpha, beta, gamma. Yeah. Alpha, beta, we'll get into that later. So you're moving from low energy to high energy particles here. So everything below visible doesn't do anything to humans. That is perfectly fine. You cell phone freaks out there, radio waves have not been confirmed. Actually, those are microwaves, but they have not been confirmed to do any damage to humans. So don't worry about microwaves. Don't worry about infrared. UV and up, that's what you have to worry about. So UV is something that over the course of a lifetime can give you a higher incidence of skin cancer. X-rays will give you a very noticeable radioactive dose, and gamma rays are the most dangerous by far. We don't really experience gamma rays in our day-to-day lives, except when you're dealing with radiation. So these are all just different. These are not hard and fast groups as to what energies they pertain to. And in my field, when I deal with photons slowing down and a shielding problem, we'll refer to them always as gammas, even though they get down into like the X-ray or maybe UV energy range. So, yeah. So let me get into this a little bit more. So photons move at the speed of light, also denoted by the constant c. They will always move at the speed of light in a vacuum. In materials, they go slower than the speed of light, and this is because there's atoms in there, and they bounce off the atoms as they go through, which causes them to appear as if they're slowing down. It's basically the average speed through a medium. So photons are always traveling at the speed of light, whereas these other things will travel at let me get into that later. That's radiation. We're not concerned with that here. All right, so that's all you need to know. These guys and up, damage, fine. Moving on. So our final particle we care about is the neutrino, and this is a very, very interesting particle. This is something that when you get radioactive decay or fissions, radioactive decay, we'll get into that in the next video, you'll get neutrinos. They like to tag along and spit out just a little quirk to make the world hard and annoying to figure out. They carry the littlest bit of energy with them. So these guys were discovered when a fission balance equation from back in the day determined to have a little bit of energy missing. So, oh God, who was it? It was Pauli, wasn't it? Pauli who predicted these. So yeah, instead of thinking there was something wrong with the math, he just predicted a new particle, basically. So neutrino. They were predicted in the 30s. It would take almost 30 more years to actually discover these guys, and that's because they're so terribly tiny, teeny, tiny, small that they're so freaking hard to find. And that's mainly because it's neutral. So neutral particles are hard to find. The photon is a neutral particle as well. I forgot to mention that. It is neutral. It doesn't have a charge. Neutrino does not have a charge. So just to quantify how hard they are to detect, say we had a piece of lead that was a light year long. How big is it? How tall and how wide is it? Doesn't matter. Just how long is all that matters. So if we had a piece of lead that was a light year long, if you were to send a neutrino through that light year long chunk of lead, it might hit one of these atoms and bounce out. It might. That's how hard these things are to detect. But that also means that we don't really care about them. They're so small that they just don't interact with matter. And just to quantify a light year of lead, this is 10 trillion kilometers, or 6 trillion miles. Crazy, huh? So that's a lot of lead. Just to quantify this, you have several billion on the order of 1 e to the 9. This is scientific notation. This means 1 times 10 to the 9th power, which equals 1 billion. You have on the order of 1 billion neutrinos. This is a times, not a minus. 1 billion neutrinos passing through a square centimeter of your skin, of your body, every second. A square centimeter, convert that to inches, 0.15 inches squared. A billion neutrinos pass through that of your body every second, and you're none the wiser because they just don't interact with matter. So don't worry about it. But yeah, that's going to wrap up my particles video, I believe, here. So thank you for watching, and I will see you in the next video, which will deal with radiation. So directly using what we learned in this video and the next video to describe radiation. So we needed to talk about these particles first. So just to recap. So first we started off with an atom, which is made of protons, neutrons, and electrons. Proton is the Z number, atomic number of an atom. Neutron is the N number, and you add these together, you get the atomic weight. Proton has a plus charge, neutron has a 0 charge. Electron has a minus charge, and an electron is 1/2000th the mass of a proton or a neutron. These make up the atom. So we also talked about isotopes. So you have like U-238 or U-235. Got isotopes, same number of protons, different numbers of neutrons. Sorry, that's off screen. We got electrons. They determine the charge. You could say the electrons determine the charge of an atom because those are the ones that are going to be moving around. So electrons determine the charge of an atom. They create ions if you have different amounts of electrons. That's useful for detecting radiation. Then we talked about photons, which is the particle of light. It always travels at the speed of light. And we also talked about neutrinos. Those sly little bastards that are hard to hit, hard to figure out what they're doing. So that about wraps it up for this video. I will see you next time. Thanks for watching. Also, the photon has 0 rest mass. Thought you should know that. Basically has no weight until it's moving. Just a little tidbit. Basically, yeah. So I will see you guys later. Thanks for watching. I'll see you in the radiation video. And we will discuss radiation. So see you guys then. Thanks for watching.